We're going to cover non-Euclidean geometry today. So non-Euclidean geometry is it's different than Euclidean geometry. What we've been studying all year is Euclidean geometry. Non-Euclidean geometry has a different set of rules. Not a whole lot different, but there's a few things that are different. And that makes, what you're trying to prove in non-Euclidean different than what the way we operate in Euclidean. So we're gonna do some elliptic, finite, and taxicab geometries. Okay, these geometries will have a different set of rules than the Euclidean. So it's kind of challenging because you have to think in a different way. But I keep things pretty simple in this chapter. If you can work the homework problems that I assign and the examples I do in the notes, then you should be fine as far as the assessments go. Okay, if you feel it's even hard for me to understand some of these non-Euclidean ideas. So if you feel like, hey, this is just way out there for me, don't panic. Like I said, just pay attention when we go over the homework, when we go over the notes, and you should be fine as far as the tests and quizzes and stuff for this chapter. Okay? All right. So first we're going to talk about Euclid. In his famous work, The Elements, Euclid stated many definitions, 5 postulates of geometric nature, and 5 common notions that could be applied to both numbers and geometry. The 5 postulates of geometric nature were as follows. Postulate 1. A straight line can be drawn from any point to any point. Postulate 2. It is possible to extend a finite straight line indefinitely. Postulate 3. A circle can be drawn with any point as a center and any distance as a radius. Postulate 4. All right angles are equal. Postulate 5. If a straight line meets two straight lines so as to make 2 interior angles on the same side of it taken together less than 2 right angles, these straight lines being continually produced shall meet at a length on the side on which the angles are less than right angles. So what we've got, what they're saying is if I had 2 lines like this, we have the transversal, angle 1 and angle 2 is, you add those 2 together, they're less than 180. If that's the case, then we know that these 2 lines somewhere will meet, okay, on that side. Postulate 5 is commonly called the parallel postulate. It was the center of much debate. For over 2,000 years, there are many attempts to prove the parallel postulate from these other postulates. However, it has been shown that it is impossible to prove it this way. So no one's been able to prove postulate 5 from the other postulates. And people have tried throughout time. Absolute geometry. Absolute geometry is different than Euclidean geometry. It's a body of knowledge that follows from the postulates preceded by the parallel postulate. So there's no postulate 5 in absolute geometry. So that does some things for us. With one of the mathematicians that worked in this area is Guillermo Saccheri. He tried to prove the parallel postulate by first proving additional theorems that did not rely on the parallel postulate. He used Saccheri quadrilaterals. A Saccheri quadrilateral is a quadrilateral having a pair of opposite sides congruent. Okay, so in this picture, here's our pair of opposite sides congruent, and 2 right angles. We've got the 2 right angles, right? The other 2 angles are called summit angles. These 2 angles are summit angles. Now in Euclidean geometry, we know those 2 would have to be right angles. Right? It'd have to make a rectangle. But Saccheri quadrilaterals are not rectangles unless the parallel postulate is assumed. So in this, we don't know that those are right angles. They're not going to be. Now you'll see where we'll come back to these, and we'll see where this applies. The parallel postulate seems obviously true because the small portion of Earth we are limited to seems like a plane. Consider the geometry of a sphere like the Earth. The shortest distance between 2 points on a sphere is an arc of a great circle. Okay, so if you think of the Earth, okay, the shortest distance between 2 points is on a great circle. A great circle is a circle of a sphere that passes through the endpoints of the diameter of a sphere. So it's the largest possible circle you can draw on a sphere. The equator of the Earth is a great circle. Alright, so in the geometry of a sphere, great circles are defined as lines. So there's a difference. Now we're saying a circle is a line. Okay, but if you're thinking about the Earth or a big sphere, then that circle would seem as if it were a line. So this is a great circle. That's a line. Here's a great circle. It's a line. These are circles on the sphere over here, but they're not great circles, so those would not be lines on the sphere. Everybody with me so far? All right. Using points of a sphere as points and great circles of a sphere as a line, we can develop a new geometry. The parallel postulate does not hold in this geometry. Consider a great circle like an equator and any point P not on the equator. Right? So there's the point P not on the equator. Then any other great circle containing P will also intersect the equator. There is no line through P that is parallel to the equator as shown in the picture. So there, the equator is a great circle. I cannot draw another line, in other words, another great circle through P that would be parallel to the equator. All the lines that go through P are going to intersect the equator, the great circle. They would all intersect. All right, so this idea of these great circles and the arc of the great circle being the shortest distance is used in a particular industry. Can anybody think of when you would use this idea? What industry would use this idea? Okay, so if you were going to fly from New York to Moscow, what part of the Earth would you cross if you flew from New York to Moscow? What's that? Prime meridian? Okay, well, like what land or water would you cross? Yeah. Okay, yeah. So he says he would cross. So he'd fly from New York over the Atlantic Ocean, over Europe to Moscow. Okay. But I don't know this for sure. But I'm just using this example. What were you going to say?
They have to fly up, so it'd be shorter.
Yeah. With this idea of the Great Circle, you actually would be shorter to fly over the North Pole, right? And over to Moscow. That would be shorter than flying across the Atlantic Ocean. So that's so the airplanes use this idea of spherical geometry or non-Euclidean geometry, they use this idea in charting their flight routes, right? This geometry also represents the Saccheri quadrilateral that is not a rectangle because B and C are greater than 90, right? So we take this Saccheri quadrilateral here. If those AB and CD are perpendicular to AD, then but angle B and angle C, there's no way those are 90 on a sphere. There's no way that those angles would be 90. Okay, so they're going to be greater than 90 degrees. Elliptic geometry. In 1854, George Riemann formalized this idea of spherical geometry by placing the parallel postulate with the following. The elliptic parallel postulate. Given a line L and a point P not on L, there is no line containing P parallel to L. So that was in that picture we had drawn in the previous slide. You can show that parallel lines do exist in absolute geometry by modifying Euclid's postulate 1 as follows. Modified postulate 1. Given any 2 points, there is at least one line containing the points. Instead of only one line, there's at least one line containing the points. Some of the results that follow from the elliptic parallel postulate are quite surprising, and they differ in that they differ so much from or actually contradict results derived in Euclidean geometry. For example, consider the figure T36. The great circles through P and Q and through P and R are perpendicular to the equator. So triangle PQR has 2 right angles. The triangle in this picture has 2 right angles. And then that can't happen in Euclidean geometry. This means that the sum of the angle measures in PQR exceeds 180. Some of the results of the elliptic parallel postulate are: there are no parallel lines, the sum of the measure of the angles in any triangle exceeds 180, there are no rectangles, if 2 triangles are similar, they must be congruent, and 2 lines intersect in 2 points. So these 2 lines on this sphere here, they intersect at P, but they would also intersect down here somewhere at the bottom, right, if they went all the way around. Any questions? All right. Finite geometry. Finite geometries are composed of a finite set of points. For example, consider the points A, B, C, and D. The set A, B, C, D is defined to be the only plane. So that plane is made up of 4 points. There are no other points in the plane. So actually, it'd be more realistic to draw A, B, C, and D all right next to each other. There's no other points in between them. So you can think of it as they're all right there together. The 6 possible pairs of points are the lines. Okay, so you can see you've got 1, 2, 3, 4, 5, 6 possible lines. So the line AB in this geometry consists only of the points A and B. In Euclidean geometry, a segment AB has an infinite number of points between it. The pairs of points are lines in this geometry. No segments connect them. Everybody have it? All right. Next, we list three postulates that this example models. There are exactly 4 points. Postulate 1. Postulate 2. Every pair of points is on a line. Every line contains a pair of points. We can deduct several theorems from these postulates. Theorem 1. If two lines have a common point, they have exactly 1 point in common. So like AB and AD, those are two lines with a common point A. There's only 1 point. A is the only point they have in common. Theorem 2. There are exactly 6 lines. Theorem 3. Each point contains exactly 3 lines. Because it's going to touch 3 other points. And theorem 4, given a line L and a point P not on the line L, there's one and only one line parallel to L that contains P. So if I have A, B, C, D, if I've got the line, we have A, B, then there's a point D, okay? There's only one line that D can be in that would be parallel to AB, and that would be DC. Same thing with the point C. There's only one line DC, that's parallel to AB that would be in it. So anyways, in the 4-point geometry described by ABCD, let the pairs AB, AC, AD, BC, BD, and CD be lines. These points and lines satisfy postulates 1, 2, 3, so they represent a model for 4-point geometry. Using pairs of letters as lines, this model verifies theorems 1 through 4. The proof of theorem 3. We're going to prove that in 4-point geometry each point contains exactly 3 lines. So let's start off by listing our lines. We have lines that the lines are pairs of AB, AC, AD, BC, BD, and CD. Those are my lines. Alright. So how can we show that each point appears in exactly 3 lines? How could I go about doing that? What would I do? Sam, why don't you get your head off your desk? How would I show that a point is in exactly 3 lines? All right. Well, we take a look. Take for example point A. Well, you can make a list. A appears in AB, AC, and AD. B appears in BC, BD, and AB. Right? C appears in AC, BC, and CD. And D appears in AD, BD, and CD. Alright? That's all there is to it. Make a list. Any questions? Alright. Now we're going to do taxicab geometry. With taxicab geometry, in Chapter 8 we found the distance between 2 points using the Pythagorean theorem in the form of the distance formula. In a coordinate system, there's another way to measure distance. Imagine a grid coordinate as intersecting streets, north-south streets and east-west streets. In taxicab geometry, the taxicab distance from PQ is the shortest distance a taxi would travel along the grid of intersecting streets. Alright, so you can the taxi can only make right angle turns. So it can either go east-west or north-south. It can't go diagonally. In the figure, PQ in taxicab geometry would be 3 plus 2, which equals 5, indicated by the dark line segments. In Euclidean geometry with the distance formula, we'd have 3 squared plus 2 squared equals the distance squared. And that's how we'd get the distance. In this geometry, the points, lines, and planes are the same as Euclidean geometry. Just the distance has changed. Taxicab geometry satisfies many of the same postulates as Euclidean geometry, even the parallel postulates. Alright. So everything's the same except distance in taxicab geometry. Something that doesn't hold is the side-angle-side congruence postulate in taxicab geometry. Take, for instance, the triangles ABC and triangle DEF. With taxicab distance, AB equals 2 and AC equals 2. These distances are 2. In taxicab geometry, in this triangle down here, DE is equal to 2 as well. 1 over, 1 up, so it's 2. And DF, 1 over, 1 up, is 2. Because the triangles are right triangles, they should be congruent by side angle side. Because they're right triangles with legs of 2. But they are not the same size, therefore they are not congruent. This demonstrates that side angle side congruence does not hold in taxicab geometry. Does everybody see that? How, by side angle side, we have the side of 2, a right angle, and a side of 2. So if the side angle side postulate held, these two triangles would be congruent, EDF and ABC, but they're not. So side angle side doesn't work in taxicab geometry. Let's apply some taxicab geometry. Find the circle. The circle's in quotes because it may not necessarily look like a circle that we're used to. Find the circle with center O and radius 2 in taxicab geometry. Somebody give me a point that would be on this circle. Has a radius of 2. Yes.
1, 1.
Yes, very good. 1, 1. is on the circle. So we can plot that point. It's 1 over, 1 up. That's a length of 2. What else? Give me another point on the circle. Sam? Yeah, 1 over, negative 1 down. All those combinations of positive negative 1 and positive negative 1. Those are all taxi cab distances of 1. Right? So we could, if we connect these points, our circle is going to look like actually going to look like a square. A circle in taxicab geometry looks like a square. What are some other possible points on this circle? So we have points positive negative 1, positive negative 1. What would be some other points? Can anybody give me another example of a point on the circle? Alright, we can take, how about if we did 1/2 over, 1.5 up? 1/2 over, 1.5 up. Like that. That is a point on the circle. And any combination of 1.5, a half, or half and 1.5. So, also, we've got 0.5 plus or minus 0.5 plus or minus 1.5. And so on. All those points. And so on. Okay? Any questions? Okay. All right, let's ignore, we're going to do A. Okay, A on A. Ignore this line here. Ignore, don't, this isn't part of it. Ignore that. So we've got to find all the points equidistant from negative 1, 0, and 1, 0. Okay? All the points equidistant. What would all the points equidistant from those points be? Yeah. Exactly. It's all the points on the y-axis. Because 1 and negative 1 are the same distance from the y-axis, and then any point along the, if we're doing taxicab distance, any point along that line would be, the 1 to the line and then plus however far up or down the line goes. So it's all the points on the y-axis. The distances, we could express those distances be all a distance of 1 plus the absolute value of y. All right. Questions? Okay. Now let's do all the points equidistant from 0, 0 and 1, 3. All the points distance from 0, 0 and 1, 3. So we kind of have to break it down here. Just one single point that would be equidistant taxicab wise from 0, 0 and 1, 3. Give me one point that would be equidistant. Braden?
0.5, 1.5.
Yes, 0.5 and 1.5. So that's a particular point. Okay. So that's going to be right here, because it's a half over and a 1.5 down from 1.3, and it's a half over 1.5 up from 0.00. So that's an example of a point. What about any other ideas? Eli?
All points with y coordinate
With what?
2. Y coordinate
Y coordinate what?
2.
Y coordinate 2. So that would be all the points on this line. No, you're doing the ones equidistant from 1, 1 and 1, 3. We're going from 0 and 1, 3. This is 2 from that line, and this is 1. You know, like if I picked this point right here, it would be 2 up, 1 over, 3 from 0, 0, and 1 from 1, 3. So that doesn't work. Any others? How about the point that's given there, 1, 1, right? The point 1, 1. It's 2 from 1, 3, and it's 1 up, 1 over from 0, 0. It's 2 from 1 from 0, 0. So point 1, 1 is 2 from those two. What other point would be 2 from those 2 points? Yes. Yes, 0, 2. So 0, 2 would be another point equidistant. That's a 2. If I put my thing all right. All right? So we've got, first we have 1, 1 and 0, 2 are both a distance of 2 from 0, 0 and 1, 3. Then Braden has already given an example. Any of the lines on this segment between these 2 points, any of those points are going to be equidistant, right? So we could say all the points on the segment between 0, 2 and 1, 1 they're going to be a distance of 2. Alright, now, what other generalizations can we make? What other points would be equidistant from those 2 points? Eli was on the right track when he said all the points on y equals 2. Okay? There are some lines that we could draw, but it's not well, he was correct when he said, except for it's less than all the points on y equals 2 less than 0. So if we drew this line, come on, and just move my thing over here. Let's do it again. Well, what happened? So we had that line, and then like Eli said, if we're as long as it's less than 0, any point on the line y equals 2, right? Because we go from to get to this point right here, this point 0, 2, we would go up 2, and then any point on this line, right? Any of those points. And then from 1 to 3, 1, 3 to that point, we go down 1 over 1. That's 2. Then any point on that line in that direction is just going to add to either one of those distances. So we have, for x, so the third thing we have is for x less than 0, all points x2, right? That covers that. What other ray can we have that's going to be equidistant from those 2 points?
1 equals 1 when x is greater than 1.
Right. Good. So we've got this direction right here. So the last part we got for x less than 0, or greater than x greater than 1, all points x1. All right, any questions on the notes? No questions. Okay.